But it's not the only part of the motor cortex. There is also what we call a supplementary motor area, which is also called the secondary motor area. And this has more influences on left and right side, both sides. So when neurons in the supplementary motor area are activated, you will tend to see recruitment of muscles in both sides of the body, whereas usually with primary motor cortex, it is only the opposite contralateral side that is activated. And then the premotor cortex is more like primary motor cortex in that it seems to be mostly contralateral, but it's not as directly connected to the spinal cord and seems more important for organizing the activity in the primary motor cortex. Now, the other part of the system, of course, that we're interested in studying is the brainstem. And in the brainstem, we have reticulospinal system. So the reticular formation of the brainstem is where we find neurons that make reticulospinal cells that also go to the spinal cord and influence movement. And the reticulospinal cells also tend to have influences on both sides of the spinal cord. So if I get, for example, into the left side of the reticular formation, and I study there and do electrical stimulation, I will find that the left and the right arm are both responding to activity of neurons in one side of the brainstem. So as you can see, there is a lot of potential for connection in this system, so that, for example, if I have an injury to my left cortex, I should have a lot of trouble moving my right arm. But because of these other pathways through the brainstem, there's still multiple alternative other pathways from the right cortex to the right arm, and whatever areas in left cortex perhaps were spared may not only have their spared connections to the right arm, but may also have some ability to work through the brainstem to also control the right arm. So we think that this system is part of what helps us recover from stroke, not just the recovery of the damaged area in the cerebral cortex, but also the person learning to use these other systems that were already there in their brain, and to learn to control them more with voluntary control to produce movement. So here's a little bit of data that we collect from stimulating in the brainstem to give you an example of how we can see that it controls both arms. So the idea is that we have a microelectrode in the brainstem, and we do these experiments with monkeys, and we can stimulate with electrical stimulation in this electrode, and we have EMG electrodes set up in muscles on both sides, 12 muscles in the left side and 12 muscles in the right side, so that we can record the muscle activity in response to stimulating the brainstem and see which muscles respond. And what we have shown in gray is the raw EMG, and in black is smooth data to make it easier to recognize the responses. And the red and blue boxes show us significant responses that pass our test. And as you can see, we have multiple muscles responding in both the left and the right limb for stimulation in one side of the brainstem. And the typical response we see would be ipsilateral limb flexion. So if we had, in this case, the stimulating electrode from the right side, we would see right arm flexion and left arm extension. So this diagram shows you a cartoon to give you the idea of what is most common in response to brainstem stimulation. So the idea here would be to imagine that we always stimulate it on the right side in the reticulospinal system.